This talk is about LLM-generated logic programs and their inference execution mechanisms. The code of everything that I will show you is available online. All the links are in paper. So LLMs as knowledge stores ready to be mined. Well, LLMs are highly compressed knowledge repositories. Our usual anthropocentric approach is when we interact with them, chat, get knowledge snippet, and then trust it. But our approach here, as you will see, will automate the process. We'll extract knowledge in the form of a logic program, a focused, goal-driven approach, a recursive exploration to unwrap the knowledge centered on a topic chosen by the user. The framework is called Deep LLM. Deep LLM automates step-by-step reasoning in an LLM dialogue thread by following what horn clauses actually do, exploring alternatives or OR nodes, and expanding details and nodes up to a given depth. So we start from a single succinct task-specific initiator, and then we steer the automated dialogue thread to stay focused on the task by synthesizing a prompt that summarizes the depth-first steps taken so far. So we use also semantic similarity to ground truth facts or oracle advice from another LLM instance to restrict the search space and validate the traces of justification steps returned as more focused and, of course, trustable answers. There are several use cases, and a particular interesting one would be a topic-focused exploration of scientific literature, but more mundane steps like guidance to achieve a goal, and also very good causal explanations are possible within the same framework. Here's an example of the Streamlit-based Deep LLM app. The question is computing stable models of answer set programs. It's a scientific concept explorer. And we'll have here the horn clause view. You would see the OR nodes here. So computing stable models of answer set programs would involve logic programming solvers or non-monotonic reasoning mechanism or grounding and solving processes. And then there is an expansion of each of these. You see here an AND node for non-monotonic reasoning mechanisms, for instance. And at the very end, we get several facts at the point where we cut the depth level, because this can go very, very fast, and the storage in the knowledge base of the LLM is deep. Abducibles at the limit. So when SLD resolution, close selection via unification is replaced by this LLM-driven dynamic close head creation with an option on, for focusing on proximity of embeddings to ground facts. That's mimicking the SLD resolution process, but it actually creates things by mining the LLM's knowledge base as we progress. There are more details in the paper about that, but when the depth limit is reached, the items on the goal stack are interpreted as abducibles, statement that can be hypothetically assumed and then checked against integrity constraints. An interesting surprise here, there are dual horn clauses also, and they have a bit neglected, partly because they're very similar to the horn clauses structurally. So a dual horn clause is a disjunction of literals with at most one negative literal, or exactly one if it's a definite dual horn clause. And we particularly like this implicational form here. If P0 is true, then P1 or Pn is a consequence of that. So what this can do is explore the known to be false. Well, we have the usual database approach in which if it's not in the database, then it's false, and the closed world assumption that dominates still the thinking in logic programming. But what we can do here, and especially because the LLMs can provide positive facts and facts known to be false, with equally large generosity in terms of quantities and depth. And that makes it kind of interesting to explore a falsification process, showing that if you assume something, then the consequences of that would be very negative, and then you have to consider that assumption as being false. This all fits actually into an intuitionistic logic framework. We don't need to get to a stronger logic like classical or even the underlying logic of ASP, which is an intermediate logic between intuitionistic and classical one. The objective of dual horn clauses, dual horn programs, is to describe constructively why something is not true. So falsify the initiator goal by backpropagating from its negative, undesirable, unwanted, harmful consequences. And here's an example. Losing the Fed's independence, which some politicians sometimes contemplate, has negative consequences. And you can see them here. Increased political influence on monetary policy, short-term economic manipulation, and then erode the investor confidence and so on at level 2. So it shows the negative effects digging deeper. So that maybe suggests that it's a good idea to leave the Fed's independence as is. Deep QA, exploring the tree of follow-up questions. After you start from an initiator question on a topic, the app is generating a tree of follow-up questions up to a given depth. So what you get as output, again, as a logic program, is a definite clause grammar that can be imported as part of a Prolog program that encapsulates that generation of follow-up questions coming with their answers and other follow-up questions. So with this, you put the LLM into an automated self-exploratory mode in which you ask, like a human would do, right? Follow-up questions to what you would argue about. And you try to predict those follow-up questions. And by predicting them, maybe your current answer would be a bit more constrained, more precise, less hallucinatory, because you are thinking ahead to the follow-up question. That's what humans do, and that can be, and is actually implemented in this variant of deep LLM that generates definite clause grammars. Here's an example. how constructive negation works in logic and constraint programming. Curiosity. You can choose the LLM here. Works relatively okay with local ones, but the quality is less. You would see a question here, an answer to it, another answer. So you would see that chain of thinking forward that's imposed on the LLM. There are more examples in the paper, and this is actually available online to explore directly. We can also generate relations, and the minimal model of the program can be turned into a relation graph. Let me, in the interest of time, show you also the situation when you have noise effects. Well, the minimal model of LLM-generated horn-close programs encapsulates facts and their consequences elicited from deep LLMs initiator queries in the form of natural language sentences. We don't dig deeper in the natural language sentences because, well, they're understandable and they are also very friendly to vector stores, and they can be matched against slightly similar sentences that exist in a vector store. So given a logic program that performs symbolic reasoning relying on a ground fact database of such sentences, an interesting form of abductive reasoning emerges here. When hitting an undefined ground sentence intended as a query to match database facts, we can rely on vector embeddings of the sentences of the query and the facts in the vector space as a good enough match, provided that the semantic distance between them is below a given threshold. And in NatLog, that's my Prolog dialect, simplified Prolog dialect. This can be implemented very easily by just overriding the default database interaction mechanism. So by contrast to the usual exact unification-based answers, this embedded language in NatLog that's called softlog works well when the query is close enough to a matching entry. So here's a little example. Question, what did Wilde say about temptation? I can resist anything except temptation. So Wilde is enough here, kind of sketchy information, and this comes back. What did Alice say about following advice? I give myself very good advice, but I very seldom follow it. And that's said by Lewis Carroll, but the connection is made between Carroll and Alice, and this semantic soft link brings an answer to the question. Well, some execution mechanisms that, unfortunately, because of the time limitations, I will not be able to go over. But we have a fast symbolic fixed point manipulation, and there is also a very nice implementation using tensors that's sketched in the paper. There is also, of course, the Katsumi Inoi's invited talk that will tell you the best algorithms for using this algebraic representation of logical reasoning. And my conclusion, well, generative AI is a major disruptor, not just of industrial fields, but also of research fields. And results produced by dominant techniques in various fields have become replaceable by much simpler applications. So that motivates our effort to join the disruption and explore several new ways to elicit the knowledge encapsulated in the LLM's parametric memory as logic programs, together with an investigation of their optimal inference execution mechanisms that are detailed in the paper. Well, we hope that this effort has revealed some natural synergies between generative AI and logic programming tools. Thank you very much.